Okay, so the next problem we're going to look at is going to be sample problem 16.4. Here we have a pulley, and that's what you see here. It weighs a total of 12 pounds, and it has a radius of gyration of 8 inches. Okay, radius of gyration. Now, radius of gyration is a value where, in this case, you're going to notice that this is a pulley. So I'm gonna kind of zoom in here a little bit. And all we get is a front view here. But if you can imagine, because there are two weights that are being hung from this, the smaller portion here has to be like, if you would, out of the screen towards us so that we can wrap the string around here for weight B. And then on the outside, there's going to be another groove where the strand for weight A is going to rest inside of. So this is not a piece of material, if you would, for this pulley that is an even cross section through the whole thing. So what they do is they give us the radius of gyration for which we could place the total mass at a distance from the center of rotation. And that's what they're giving us here for 8 inches. So you'll notice that this has a radius of 10 inches total. They're saying if we would go 8 inches out, that would kind of like be, if you would, the center of gravity for where the radius of all the material could be concentrated at that point, and we can consider that, a radius rather than the very outside, okay? When we have a disc, for instance, that is of the same cross-sectional material and the same thickness, then we can use the dimensions from the actual problem, and we'll see that in I think our next sample problem. But when we have something that the cross-section changes throughout, the problem will give you this radius of gyration. Now, when we're given radius of gyration, we are going to use it to calculate our moment of inertia. Capital I is going to be equal to mass of that element times the radius of gyration, which is K. Okay, in this book, they're using the symbol K, and it would be squared. Okay, so any problem where you're given radius of gyration, K is going to be the variable for that. And we multiply it by the mass to get the moment of inertia for that shape. So in this case, for this pulley, we would use the mass of the pulley times the radius of gyration, and that's going to be the value we get for what we call the moment of inertia, the mass moment of inertia as it rotates around. On the other hand, if they were not given the moment of inertia, that means that we're dealing with something that has an even cross-section. And in the case of the next problem that we do, it's going to be a disc that is of the same material, same thickness. It would be 1/2 times the mass times the radius to the outermost material squared. Okay, so the difference here is that K is radius of gyration. And in the case of the second one, R is going to be the distance to the outermost material. Okay, that's when we have a thickness that's all the same disc. All right. So we are going to be using moment of inertia is equal to m times K squared because we're given radius of gyration here. Now it says assuming no axial friction, so we're not worrying about any drag as this rotates around. They want us to determine the angular acceleration of the pulley and the acceleration of each one of these blocks, okay? Each one of these blocks. So let's kind of start out. I'll go underneath here, okay? This is sample problem 16.4. Now here again, we want to put our convention in the upper right-hand corner. Okay, our normal convention to the right and up is positive and counterclockwise is positive as well. We're given the weight of that pulley to be equal to 12 pounds. Okay. We also know that the radius of gyration, K, of the pulley is equal to 8 inches. All right. Now, as we know, when we're working with English units, we want to have our distances all in feet, okay? So we would do a quick conversion here. We would say 12 inches in 1 foot, and this radius of gyration is going to be equal to 0.667 feet, sorry, feet. Okay. Even though we won't be putting feet in our equation, which kind of kills me, but again, we would be really long in some cases with things and it gets a little confusing. Just make sure that we have pounds and feet and seconds for our units, okay? So anywhere there's a distance, if it's inches, we gotta convert it over. All right, and then find, okay, what we're gonna find is going to be the angular acceleration of the pulley, okay? And then we need to find the acceleration, straight line acceleration of block A and the straight line acceleration of block B. Okay. All right. So we're going to draw our diagrams first. Okay. Now, these are circles, so I'm not going to draw the circles, but what I'm going to draw is, I'm going to draw a straight line, use my protractor here. I'm going to draw a straight line, okay? And the left side here is going to be where the block B pulls down on the end. And then the right-hand side is going to be where block A pulls down. And then if you look at the distribution, our G is going to be closer to B, okay? Okay, so this is going to be point G. So this is the center, if you would, of rotation. A is further out and B is closer. B has a radius of 6 inches, okay? So that means its distance is 0.5 feet, okay? And that's from the center of the rotation, or the center of gravity and rotation, G. And then from G to A, that's 10 inches, that's 0.83 feet. Okay. Now, forces. We do know that the weight of our pulley at the center of gravity, we can concentrate that 12 pounds, right? Coming straight down. And then as a reaction, we would have the reaction, if you would, of R going straight up, because that's where the support, if you would, for that whole pulley is. We also know that block B going down is 10 pounds and block A is 5 pounds. Again, both of those are directed downward because those are blocks that are hanging. Okay. So that's our static side, the forces, the external forces that are present. We're going to set that equal to, and now we're going to draw kind of that same illustration. Okay, the A, the B, and the G going across. So B, A, and then G is right about here-ish. Okay. Now, this is the inertia side of things. This is looking at the mass. Now, each one of those blocks are going to be going up and down, all right? So if we look back at the illustration, the pulley is going to rotate, but the blocks themselves, remember, we have to find the acceleration of each one of those blocks. Those are going vertically, right? Those are going translationally. So we are going to show, and if we look here, we're going to show MB times AB. It's going to be right here, going in a downward direction. Okay. And then you're going to find that if you compare it to in the book, just for a moment here, bear with me, we're going to put the MA times acceleration A. Okay. Now, if you assume a direction and it's not correct, your math will tell you if you're right or not, just like it did in statics. So don't worry, you want to have a direction here. You might say, well, it's hanging down, it's going that way, but, if we look here at that illustration, okay, and I want you to think statics moments for a second, all right? So if we take 10 pounds and we multiply it by a radius of 6 inches, what do I get? 60, right? On this side, I get 60 as my moment on the left-hand side. If I take 5 times 10 inches, what do I get? 50. So 50 on the right, 60 on the left. B is going to go down. What's going to happen to A? It's going to go up. That's why when I go underneath here, that's the direction of the mass and the acceleration for A. Okay. But again, if you wouldn't put it in the right direction, that's okay. It'll kind of come out. Now, additionally, this is rotating around. The pulley itself is rotating around. So we need to add moment of inertia, mass moment of inertia times the angular acceleration of that pulley. Okay, so this is the angular acceleration of the pulley. This is a straight line of A, straight line of B. Okay, so these are the ones that we're going to want to calculate, or we're going to need to calculate, right? And it kind of makes sense. This is going to be going like this, right? Based on the forces. So then the pulley is actually going to go in that direction as well. So you kind of get that sense based not only on, you know, the way that we put that in there, but also the way that the rotations are. Okay. So now the next thing that we're going to do is we're going to start by looking at and trying to calculate the accelerations of those blocks. Okay, so now as we look at the illustration that's up here and just looking purely at the accelerations, okay, and not worrying about the masses. So just kind of imagine that the masses aren't here. They kind of, if you would, are going to be irrelevant, but we want to look at the directions of the accelerations and the angular acceleration. So maybe I should draw it. Do this. I think I do need to. I think it'll help. Thinking back to kinematics, okay, kinematics, and I'm going to draw a smaller circle in the inside here. All right, so the outer is the larger portion of our pulley, and the inner is going to be the smaller portion. I know that this is this is point B, and this is point A, right? Center of rotation is right here, or the center of G, okay? We know that this is rotating in counterclockwise direction. So that's our alpha. So I'm just looking at accelerations right now. And I know that my acceleration of B is going to go down, just like we had talked about just earlier here, B. And I know that my acceleration, A, is going up, okay? Now, the point and why I wanted to draw this here is, do you see how these are on the outside edge of each one of those circles? So as I rotate around, remember there are always two components of acceleration. There's the normal and the tangential. Which one, normal or tangential, are A and B? Are these tangential accelerations or are these normal accelerations? They're tangential because they are perpendicular to what would be the radius going back, and our normals would normally go in the inside here, right? Now, this is another equation that you're going to want to add to your equation list. And this is kind of like going back and kind of remembering kinematics, if you would, okay? We know that a tangential acceleration is going to be equal to the angular acceleration times the radius. You may like, oh yeah, that vaguely sounds familiar, but we did learn that back in kinematics. So tangential component of the acceleration is going to be equal to the angular acceleration times its radius, or its distance away from the center of rotation, okay? So since B is a tangential and so is A, we can say then that, make sure I get what I need here, we can say that acceleration of B is going to be equal to the angular acceleration times the radius to B, okay? So B is going to be the distance from here to here, and we know that to be 0.5 feet. It was 6 inches. So we can say that AB is going to be equal to, the radius is 0.5 times angular acceleration, okay? So this is the tangential component at B of the acceleration in terms of the angular acceleration. And then we're going to do the same thing for A. Acceleration at A is going to be alpha, which we don't know yet, which is okay. It's going to be the radius to point A. And we know that to be 0.83 feet. So acceleration at A is going to be 0.83 times alpha. Okay. Now, the other thing that I do have here is I know that A is going to go up and B is going to go down. Now, the next thing that we want to do is we want to get and calculate the moment of inertia of the pulley because we're going to need it for that calculation. So down here, I've got a little bit of room, okay? This is simply going to be the moment of inertia of the pulley using the data that it gave us. There's an E in there, okay? So we know that I is equal to M times K squared. Again, K is that radius of gyration because this is not like the same cross section throughout. They're giving us the value of the radius of gyration. So we know this to be, now we don't know what the mass is, but guess what we do know? We know the weight of that pulley, right? So if we know the weight of the pulley is 12 pounds, we're going to divide it by gravity because we know that mass is equal to weight divided by gravity. So I'm just going to put that here. Mass is equal to weight divided by G. Okay, so that's going to be the mass times the radius of gyration, which they told us was 8 inches, but we converted it to 0.66 feet, so 0.667 feet times 0.667 feet. You don't have to put the units in there. Okay. So now if we multiply this out, oh, sorry, you have to square that. Don't forget to square it. Our I is going to be equal to 0.1658. Okay, and again, we're going to use that in the next equation. I just kind of calculated it here since that way we have a number rather than putting that all in the equation below. Because it'll get long enough. Okay. All right, so now the next thing we're going to do is we're going to use that sum of the moments around the center of our pulley. We're going to set that equal to the I alpha, MA, and perpendicular distance. Now, this is going to get a little bit longer. So this is going to be step number 4. And we're going to start with some of the moments around G, which is going to be our left-hand side here. It's going to be equal to, now we've got some things going on here. We not only have rotational motion, but we also have translational motion. So we've got to add it all in. So we're going to have I times alpha, okay, plus first going to have our mass at B times the acceleration at B times the perpendicular distance, okay, from B to G, okay? So don't forget you have to multiply by that distance. And then plus MA, acceleration at A, times the perpendicular distance from G to point A. Okay, so it's because there's 2 translational motions. If there would just be one, we would just do it for one side, but there are 2. There's different values at B and at A, so we have to add those in there. Okay, so let's do some of our moments around G and then equal to our other side. So starting at G here, I've got 10 pounds, right, times 0.5 feet. So I'm going to start way over to the left here. This is going to be 10 times 0.5. Okay, and again, that's feet. Remember, we need our distances in feet. And when we rotate, when we put our finger on G and we rotate in the direction of the force, it is going to be in a positive direction. It's going counterclockwise. We don't include the 12 pounds in a moment equation because the 12 pounds and the reaction are going right through the center here, so not included, but the other offset force is going to be at A, the 5 pounds going down. So it's going to be 5 times 0.83, and it is going to rotate clockwise, so we're going to put a minus out front here. Okay. All right, now we're going to be equal to, we're going to now start the right-hand side of our equation. So now we're looking over here. Moment of inertia, we just calculated that in the previous step. That was 0.1658. Okay, 0.1658. Here. Times alpha, right? So I'm going to put it in the parentheses here so we don't forget about it. Times alpha. Plus mass. Okay. The mass. Instead of putting it in here, we probably should calculate it on the side. I think I'm going to do that because then I can put the decimal in here. But to calculate it, we know that the mass is going to be equal to our weight divided by 32.2. Maybe I'll just stick it in here. This is going to be our weight of 12 pounds. I'm going to put the pounds on top here. Divided by 32. Oh, no, I'm very sorry. B is 10 pounds. I was thinking pulley. B is 10 pounds. Because this is the mass at B for that block. Sorry about that. Divided by 32.2. Okay. Times the acceleration at B. In the previous step, we found the acceleration at B to be 0.5 times alpha. Okay. So we're going to put that substitution in here. So this is going to be 0.5 times alpha. And then don't forget perpendicular distance from G, because we're summing our moments around G, to B, which on the left-hand side here, that's 0.5. Okay. Plus, now we're going to do the mass of A. So that's going to be 5 pounds divided by 32.2 times its acceleration, its acceleration at A, 0.83 times angular acceleration. And my perpendicular distance from G is 0.83. 0.83, 0.83. Scooch it in there. You guys see that? So 0.83. Okay. So now you want to do the algebra and the math here. Okay, so go ahead and make sure that as you go through here, you have your unknown variable. The only one unknown variable we'll be able to solve for now, alpha, because it's our only unknown. We can combine, the alpha terms here and then solve. So I'll kind of do it step by step, but I'm going to let you guys work in the background. I'm going to write mine here. So you should get 2.38, and the units for angular acceleration are going to be radians per second squared. You may remember that from kinematics, but I know we didn't put all the units in. But again, you can see how much longer this would be. I'm already using the full width of the paper. But trust me, radians per second squared. Oh, how different, I mean.
I got minus 2.43. Same thing. Positive.
Yeah, it should be positive. You got what? Tell me the number again. 2 point what?
2.4.
2.4, I have to believe. Oh, I could rerun my numbers. You got my number? I'm sure it's the rounding and that you got the same thing as I did, James?
Yeah.
Okay.
I didn't do any.
You didn't do any rounding? Yeah, throughout. And if you did it through, yeah. On my calculator, I have to, I think I do it like 4 or 5 decimal places.
I pretty much have everything that's the same, except I minus 0.85 on the left side.
On the left side, it should be 5 minus, yep, I have that right here.
And 5.
Oh, you have 4.15. Again, I think it's a little bit of rounding, Aaliyah, so that's okay.
Yeah, how did you get 0.835? I got 0.85 on the left side of the bottom. That might be a part of it.
Which one?
Where you have 0.835 on that part, right before you get the answer.
Right here?
Yes, there. I have 0.85.
Oh, do you?
Yeah.
Yeah, I'll check. Hold on, let me see. Yeah, so we're within. So 4.165 minus. Yeah, I get that because I have 4.165 on top. Aaliyah said she got 4.15. So again, I think it's just a little bit of rounding. So just within reason, and that's when I look at your answers. I'm not looking for exact, right? So because everyone's gonna put it in their calculator a little bit differently and round at different places as long as, right, you're pretty darn close here. Okay, so that's our angular acceleration. That was one of the variables they wanted us to find. So if we look back over here, this is our alpha of our pulley, okay? Angular acceleration of the pulley, all right? So that one's done. Now what we want to find is the acceleration, the actual value of the straight line acceleration at A and the straight line acceleration at B. If you recall from the previous page, down here, we have each one of those accelerations in terms of the angular acceleration, which we just calculated. That's what we're going to do is we're just going to plug in the value for our angular acceleration to get the straight line at B and the straight line at A. So here are going to be our accelerations. So we're going to have AB, it's going to be equal to 0.5 times our angular acceleration. I'm going to do my 2.38 because that's what I got. Okay, so our acceleration at B is going to come out to be 1.1938, and that's going to be feet per second squared. Make sure you put your final answers with their units, and the direction of B is going to be down. Again, it's a vector quantity, so make sure you put the direction. And then the acceleration at A is going to be 0.83 times alpha. And that's going to be times the 2.38. And then my acceleration at A, 1.9825 feet per second squared. And that one, as we know, is going to be going up as this rotates. And this should be pretty close to what they have in the book, if I remember. Yeah, so the book says our alpha 2.37, okay? The book says 1.1978 for A and 1.187 for B. So again, very reasonably close to each one of these. Yeah. So questions on the problem here? Okay, I'm going to stop the recording.